and all of these amino acids of the 20 get all paired off in the right way and make the right structure for a protein, and it just goes on and on. So what's a protein? Well, it's composed of hundreds of thousands of what we call peptide bonds. I'll tell you what a peptide bond is in a minute. Okay? It's encoded in long helical coils or sheets or a combination of both. In other words, if you think of these long coils like DNA or RNA and just keep entwining them, numerous ones, not just a pair or just a single, but numerous ones, and then add on to that sheets of groups, all coming together to form a unit, a big unit. That's going to become a protein. They all came together by forming what's called bonds between the amino acids. Those are called peptide bonds, okay? The particular amino acid sequences and the geometric structures in these proteins determines the function and the biological activity of a particular protein. The folding geometry of the protein is crucial, let's say most crucial. The folding geometry, after it's all put together chemically, the way that big unit folds together determines how it functions, okay? It's crucial to its function. So all you do is change the folding geometry of a protein. It can have the same structure, chemically speaking. It can have a different function altogether. All right. Here are some very colorful examples of proteins. Now, these are not real proteins. These are chemical models. They use these sticks and color units and so on to try and give a overall description on how the complexity of these amino acids joined together would fit in these proteins, okay? So this is just representative. It's not. If you looked at a protein structure under, say, an electron microscope, high resolution, what you would see is a lot of outlining and shadowing of units that are lighter or darker. You don't see any color at all, of course. But so the atoms and the way they join together, you see that looks like hills and mountains and units like that. That's what you see. Like you're looking at a topograph, something like that, or an aerial photography, right? Something like that. But that's what you actually see. But this is just to give you an idea. So see, each one of these color codes is a different strand of a protein structure that's joined together. Here we got them joined together and folding around into a circular system. Here we got them spreading out into coils. Here, okay? Here we got them all joined together and bunched up like a ball. Different sequences of amino acids, the red ones and the green ones. Here we got a whole bunch of coils, different ones, blue ones, the light blue ones, the green ones, the red ones, and these purple ones are some other groups in there, usually metal atoms or something that are in there, and they play another dynamic role like hemoglobin and chlorophyll and all that stuff is a whole other story in this whole game. And then here's some bridge structures like this, just to give you a rough idea of how they're going to come together, okay? Now this next slide is not working, so I'm just have to bypass it. It was a video, and it's a great video, but it's not working. So maybe we'll get it working sometime, okay? Now, in spite of all of this complexity, which I've just shared with you, in spite of this, of course you can say, well, some of this is more recent information than we had previously, right? Which is true, but they had a good bit known about it back in the 50s because the structure of DNA by Watson and Crick was determined back in the 50s, okay? So they knew something about complexity then, even then. Nonetheless, the renowned scientists such as Stanley Miller and Sidney Fox and Philip Urey, these renowned people, University of Chicago, University of California, wherever, did laboratory simulations of experimental chemical reactions which they proposed mimic the environment of a primitive Earth. They believed that the Earth in its early stages was a reducing environment. Now it's not reducing. Why? Because it has oxygen in the atmosphere, right? Mostly nitrogen, but roughly 25, 75%, 25 oxygen, 75 oxygen, just roughly, okay? Now, many others have subsequently repeated those experiments, widely varying conditions, in efforts to form legitimate peptide bonds. That was the whole idea. What was the thinking? If we can produce amino acids with these simple reactions under these conditions that we believe existed, okay, natural conditions, right, that we believe existed, then we can get these amino acids to join together and they will form these peptide bonds and they will produce proteins. Then we're off to the races, see? But you notice I just showed you some things that were very important about what we know. The proteins don't stand alone, do they? They're right in there with the DNAs and the RNAs and everything else that's acting in a synergistic sort of fashion. There's a synergism there, you see? So to just isolate a component of the whole biological process and say that part of the chemistry is going to give us insight to evolution, that's going way out on a limb in the first place. But believe me, it got a lot of recognition, and it still does. It still gets a lot of recognition. Okay, the question is, how valid is that? Well, here's what they did. They took this apparatus, got some boiling water here. This is called a liquid trap, where they can trap some stuff that comes down. And over here you got a cooling condenser. Water circulates in it. Okay? Up here's your reaction vessel. You're going to pump in there methane, CH4, ammonia, NH3, water, and hydrogen gas. Okay? Nothing oxidizing in there really, because water's not called oxidizing. Okay? A spark discharge or an electric arc discharge, they use different mechanisms, high energy, activated all these gases, okay? And then they let it go. They let it react, and they collected the components, all right? Okay? So the reaction contains ammonia, methane, hydrogen, and water. Notice oxygen and nitrogen, which make up the present atmosphere, is not in that mix, because they didn't believe that was the early Earth. Okay? It didn't appear then. So it was presumed that it was a reducing atmosphere, as I said. The reducing atmosphere is essential, important word, for amino acids to form, because an oxidizing atmosphere destroys